Come on, crazy dancer, music is the answer. Do, 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 do. Hey there. We're looking at a circuit setup which contains both resistors and capacitors here. Now, this is not a RC circuit, as we're going to see in this problem. The RC circuits normally have, charging curves or discharging curves. The way the problem's set up is going to be a little bit more just resistors, just capacitors. How do we think about a problem? So we've got this circuit here. We've got a 30-volt EMF. We then come out, hit a junction point to go to a 5 microfarad capacitor. If we go up, there's a 40 ohm resistor up here. To connect these back together, there's a switch which is open, and then up top there's a 10 microfarad capacitor, an ammeter here to measure currents passing through this point, and then a 20 ohm resistor down here, and then we connect all back together. Okay. Now, this question is asking us initially, what is the steady state current through the ammeter? And this battery has been connected for a long time, so it's been connected like for an infinite amount of time. And what that means is if we take a look at this here, we know current is going to come out of this battery, this EMF. It's going to come up, and it can go over, and it can continue up and around. Okay? Now, since this has been hooked up for a long time, we can essentially say that both capacitors are fully charged. And we know that when capacitors are fully charged, they're going to act as a broken wire. And that way, current will not be able to pass through them. So no current can get through this 5 microfarad capacitor. And no current can get through this 10 microfarad capacitor here, which means that there's actually going to be no current passing through the ammeter. Just nothing can get over to that side. So due to the fact that C1 and C2, the two capacitors, are full, they're going to equal broken wires. And since they're broken wires, this means that the current through the ammeter is going to be 0 amps. Okay? And that's just something that we have to know there. We have to know that whenever caps are fully charged, they're going to act as broken wires. So let's look on to question B here. What's the charge on the 10 microfarad capacitor? Well, that's nice and straightforward. If we know what the voltage is of our system, and we know it's fully charged here, we can just say that, hey, look, the charge on this capacitor is going to be equal to the capacitance multiplied by the voltage across that capacitor. And in this case, because we've got a full 30 volts here of our system, it's going to be a full 30 volts across that capacitor. That's where all of that potential drop will be to create that broken wire here. So all we need to say here is that this is a 10 microfarad, so that's 10 times 10 to the minus 6 farads multiplied by 30 volts. And anytime your capacitor is fully charged, the voltage across it is just going to be the voltage of your EMF, whatever is being supplied to it there. Okay, so for one EMF system, that's pretty straightforward. It's just 30. If you have two, you might have to do some combinations there, or things might get weird. But in this case, nice and straightforward here. 10 times 10 to the minus 6 times 30 is just going to give us, what is that? I don't know, it's some number. I never really do numbers, do I? I'm having such a brain fart this morning. 10 and 30 is 300. That's 2. That should be like 3 times 10 to the negative 4 coulombs. Why does that 3 look janky? Looks really bad. That's what we should have. Okay? So nothing too bad there. For part C, we're asked to calculate the energy stored in the 5 microfarad capacitor. And remember, that energy stored on a cap, there's a few ways we could write this, but the one way to do it is 1/2 CV squared. And like we just did in problem B, or in part B, we know that the voltage across that capacitor is the 30 volts. So we could just say here that it's going to equal to 1/2 times 5 times 10 to the minus 6 farads times the 30 volts here. And this will give us, let's see, 30 divided by 2 is 15, 15 by 5 is 75, so let's just call this 75 times 10 to the minus 6 joules for energy, okay, whatever that is. Okay, so that's not bad. That's whenever this switch here is open and these caps are fully charged and they act as broken wires. Now, we close the switch. Throw the lever, Kronk. So we throw the lever, we throw the switch, and it is closed off now. Okay? Now in our case here, our capacitors were initially fully charged, and they still are fully charged. So the question becomes, after a long time, we have a steady state current again. So the capacitors have started to discharge out here. They've discharged out, and we're asking, what is the steady state current after a long time? Well, if we think about it, current's going to come out here, and then if these capacitors were once full, if at the moment that switch is closed there, what's going on? Well, these caps are at 30. This EMF is at 30 as well. We're going to actually get current to come up, dodge this capacitor acting as a broken wire, come down in this line, and then come out this way. Okay, so we can actually just redraw this circuit here as the 30 volts, and then just in series it's going to be the 40 ohm resistor and then the 20 ohm resistor. And that's it. That's all we're going to have in this setup here. That's all that's going to exist, because the caps are still going to be acting as broken wires for us in that small instance of time. Because of this, if we want to find the steady state current through the system, we just can use Ohm's law, V equals IR. We know the voltage here is going to be 30 volts of the system, and we know the equivalent resistance. Because these two resistors are in series, we can just add them together. So 40 plus 20 is just going to be the 60 ohms, and solving for I here, 30 divided by 60 is going to be 0.5 amps. Okay. Now that's not going through the amp meter, but that is the amperage through the current itself, or through the system itself. Okay. If we're looking for the final charge on the 5 microfarad capacitor, this is actually very similar to what we did in an earlier question, in question B, where we found the charge on the 10 microfarad capacitor. But in this case, it's still just going to be that the charge equals the capacitance times the voltage. The capacitance was the 5 times 10 to the minus 6, and the voltage is still that 30 volts. That's still the voltage across this fully charged capacitor here. In this case, we'd have like 150 times 10 to the minus 6, so you could say 150 times 10 to the minus 6, or you could say 1.5 times 10 to the minus 4 coulombs. And then last but not least, calculate the energy displaced as heat. So we're looking for energy here, so we're looking for some probably power draw in the 40 ohm resistor in 1 minute. So we're definitely thinking about power draws once the circuit has reached a steady state. So once the current here is 0.5 amps. Well, if we want to do this, we know that we could write power in a few ways. PIV is one of them, but I squared R is another one, and that's the power across that resistor. If we do this, we're going to get 0.5 squared times 40. Maybe it'll be easier to write this as 1/2 squared, because now I'm going to see that 1/2 squared is 1/4. 1/4 of 40 is going to be 10, and those are units of watts, which can also be thought as joules per second. Now, if we're doing this for 1 minute, well, that is for 60 seconds. So now we see that seconds have canceled out here, and we're going to get that 600 joules, which is a unit of energy, have been used up in this time period. Okay, so that's how we can go about part F for that. We can recognize that power is equal to some amount of energy, or a work, as it's sometimes written, divided by time. So we can just simply say power times time equals that energy. And that's what we did. We said, hey, here's our power, here's our time, here's our energy. And that's it. So this was a circuit with both resistors and capacitors in it, but we didn't need any RC circuit stuff. We didn't need any of that calculus or those curves going on, simply because since the capacitors were fully charged, we could think of them as broken wires, and understanding what happens when those caps are broken wires is very important for the system. Remember, if these caps were uncharged, they would act as shorts in the system. They'd act as just wires. So if they were uncharged and we threw the switch, we'd actually get current coming up, going through the 5, going up, going through the 10, and then darting back down through the amp meter and coming out. But that would only happen for an instant before those caps started to charge here. But in this case, they were fully charged, and we're all set. So with that, this problem is finished. Best of luck on your circuit analysis. I'll see you later. So adios.